I'm Sarah Simon. If you haven't seen me before on any of these EESN supported webinars, I am the chair of the MIT Alumni Energy, Environment, and Sustainability Network. We call it EESN or EES Network. We are an umbrella group for educating and connecting MIT alums on the important challenges we have in our name for our changing world. And hopefully, this education and connection will help alums get together to act on environmental and energy challenges. So if everybody would please mute, since you're not part of the presentation, we are going to have all the panelists speak first, and then we'll have our discussion and question and answer afterwards. You can use the chat for your questions, etc. We are recording this session, and we are going to post the slides and the recording in a few weeks from this event. Wherever you saw the event, it's an event description page. That's where we'll have a link to the slides and the recording. So I think we might as well, I'll get started with a more formal introduction. If you would click the next slide, please. The EESN network was organized with a 2008 survey by Natalie Lorenz, the MIT Alumni Association president this year. And at that time, in 2008, the evidence was clear. Our climate was changing. I have a timeline here that I'm not going to go through, but between the time of the first survey and the Paris Agreement in 2015, students and a group of alums did push MIT to make a climate commitment. And for the network, in 2018, a group of alums in Maryland started a climate solutions group with the help of the network, MIT Alumni for Climate Solutions. And this project was to write a letter and more than 100 MIT alumni signed. It was sent to all of the Maryland candidates, and it asked them their stance on climate change action. This group became the MIT Alumni for Climate Action, MACA, in about 2018, as I said, and it is led by Shiladitya Dasarma these days. Among other things, MACA has an eye on climate commitments from MIT. And one of its groups is the MACA Campus Team. It's led by Susan Murcott, who will be running this webinar. She is a lecturer at MIT's D-Lab and one of my Course 1 civil engineering, now environmental friends. Susan has worked on international water issues in the developing world, and she also offers climate courses for MIT students. The campus team of MACA includes alums expert in innovation, heating systems, and corporate finance. The campus team learned that MIT had been working on campus decarbonization and had hired a consultant in 2021 or 2022 to prepare a holistic net zero carbon emission strategy and to implement the strategy. They had done it for several other universities. When MIT moved to Cambridge back in 1916, the buildings included what's called a central utilities plant. And this provides a network of heating pipes and electricity for the campus, sort of a district heating plan. The alumni team reviewed how the most efficient building heating and cooling systems could be used in renovations that would eliminate fossil fuel use. Modern heat pump systems, which is what they preferred, move heat energy from the energy stored in the ground or in the air to where it is needed. Or heat pumps can move heat away from where cooling is needed, and they work like your refrigerator or your air conditioner. In a moment, the campus team panel will tell you about the MACA MIT, the thermal energy network design, and how it would eliminate fossil fuel energy for MIT buildings. In comparison with the presentation of pathways that the MIT consultant has provided, this design looks like it's going to be a far lower cost and a much reduced schedule. And they also had been asked to set up a pilot test. They call it a test fit. And MIT is likely to implement this west of Mass Avenue for a few buildings, and it will prove how the MIT system will work. So just to reiterate, presentations are going to last about 40 minutes. Then we're going to open the floor to questions and comments. We have this program scheduled till 7:30 Eastern Time. And please put your questions and comments into the chat while we're speaking, but we would appreciate you all having yourself on mute until we open up the questions and answers. We're recording this meeting and we'll be posting the video and slides in a few weeks. So, Susan, take it away.
So, thank you, Sarah. I'm thrilled to have, together with my team, this opportunity to share our work with you on the MIT Thermal Energy Network, Campus Decarbonization by 2035. And the team, as Sarah has introduced us, is on the panel today is John in the upper left, and me in the center, and Rick, and finally Megan. And we've started as a MACA MIT Campus Team, and in 2023 we're joined by a what we call Geo at MIT student team, and so we've grown some in the last several years. And so 4 of us are here today to share our work, our collective work. There's 2 problems that we start with. One, MIT's decarbonization challenge. 97% of MIT's CO2 emissions are from its buildings, and 26% of all the City of Cambridge's greenhouse gases are from MIT. Second problem is that MIT's climate action plans from 2016 and from 2021 are weak in regard to campus decarbonization. As you can see in this slide from Steve Lanoux from MIT, from MITOS, MIT Office of Sustainability, MIT's Climate Action Plan 2021 has 2 parts, to decarbonize to net zero by 2026. And as you can see from this graphic, that's done by way, under the global side, by power purchase agreements, by decarbonizing the grid, which is outside of MIT's control, and by direct carbon offsets. So basically offsets and power purchase agreements. And you can see that that's starting large and going down over time to 2050. But between now and 2026, that is the main action in terms of decarbonization of the MIT campus. And then only ramping up after that, maybe in 2040 and up to 2040 to 2050, is local action paramount, where increased investment is in campus energy efficiency and in new energy era infrastructure. So there's the anticipation that there'll be innovations in the pipeline, but maybe they're not starting for a decade or more. In contrast, what the MACA Geo team is looking to do is to expedite that timeline. So on the timeline of solutions in terms of our own work, in 2016, Rick Clemenzi and his partner Judy Siglin won the MIT Climate Collab competition with a plan to decarbonize MIT. That's very similar to what we've expanded upon today. In 2021 to 2023, D-Lab students, and I'm a lecturer in D-Lab, mentored by Rick and Judy, analyzed MIT buildings toward an En-ROAD style interactive energy model of the MIT campus. So teams of my students from the D-Lab class have worked with Rick and Judy over these last years. In 2023, the Geo team, a student team, again, that arose out of D-Lab, a class of mine, joins MACA, MIT campus, and they win several DOE geothermal competitions. And in the last year, the MACA MIT campus has begun meeting yet more regularly, from monthly to weekly, to create a detailed plan to decarbonize the campus. Our proposal emphasizes energy efficiency upgrades big time right away, and decreasing over time as they are accomplished. But the the key characteristic of our plan is eliminating direct emissions by 2035, excuse me, but via the Mitten plan. Yeah.
Can I go look at it first?
You can look at it in a minute. Hang on. All right. Climate's both climate and solutions start to heat up in March of 2024. We published in 2024 a business plan and a technical plan to MIT's campus decarbonization. MACA and the Alumni Association host an event with President Kornbluth to discuss climate leadership, and she reads these plans in the context of the Q&A that occurred at that event, at that conversation. And Facilities provides a MOU, a Memorandum of Understanding, to the MACA Geo team for a test fit study to validate a possible pilot demonstration. In June of 2024, MIT's decarbonization consultant, AEI, outlines a plan of 17 pathways in a closed-door meeting, but that does invite several faculty decarbonization committees to that June event. I happen to be the one person from MACA at that event. And so the MACA Geo team is at the table, but we were not included among the analyses that AEI conducted. So we added ourselves to that analysis, and we are this final bar and arrow in this graph. What is Mitten? MIT Thermal Energy Network is a network of pipes to connect multiple buildings together with thermal energy sources and sinks. There are multiple components to a Mitten design. It can have geothermal and air. It will have heat pumps for sure, ground heat exchangers, waste heat recovery, potentially surface water, piped water networks or wastewater pipes, and thermal storage. It allows rapid decarbonization via off-the-shelf equipment. It is cost-effective and it's minimally disruptive. These reports you can find at these links. The full test fit report is an 85-page report. Summary report is a 10-page report. These are the most recent reports we've produced in September 2024. And we did, a year ago, lay out a timeline for the next 10 years that will be modified if we go forward with the test fit, which we had anticipated in an ideal world would begin by the third quarter of 2024. It has not begun yet, but we have accomplished the test fit. And so with that, I'll turn it over to John Dabels, who is our financial person.
Okay, thanks, Susan. Could you just go to the next slide? I guess we're going to walk through, as a reference point, the decarbonization goals. We had to eliminate emissions. And so if you can just keep scrolling there, that would be great. As Susan mentioned, the base MIT plan is 2050. We're looking at 2035. We want to offer practical solutions. The key was, can we use these worldwide, not just on campus, but can the system be sort of modular to use worldwide, or the idea? And then finally, had to be financially responsible. And so we're going to go through a quick review of the financials and turn it over to Rick to get into all the technical part. But as you look at this, the MIT plan, or the recommended MIT plan from the engineers, is a centralized system. We have what's called a distributed system. There's a marked difference in cost between the two. And so, is MIT willing to spend $700 million more for effectively, at the end point, the same as a user? It's the same system. You still get warm and cold in the building. So let's look at what's the difference in the $700 million. And Susan, if you can, there we go. Well, 500 million of that is the centralized system requires new pipes. And these are heated pipes, but because of that, you have to do it at most of the buildings on campus. And that's a very large expense. So the piping expense, we're going to have some extension of the chilled water loop, but look at their 500 million, and at the very bottom of the right-hand portion of that slide where it says Mitten, you'll see a little red line. That's 15 million. So that's the difference we're talking about for infrastructure. The next part is the equipment. And they're looking at the proposal is from AEI, 761 million. We're looking at 550 million. That's over a 30-year period. We will replace our equipment as well. Next slide, please. In addition, there's some, that was CapEx. Now some energy use differences. And again, we've got a huge amount of money, at least 30% savings. And I think that's on the low side. And that's $100 million or more over this 30-year period. And one more, please, Susan, and I'll tell you what that is. The sources of energy savings, we have a 2-pipe system. They have 4 pipes. We're only pumping through 2 versus 4. Negligible transmission losses. There's free energy, which Rick will talk about in great detail. And then also a higher coefficient of performance. So our efficiency is much better as well. There's what's in the budget. What we're looking at is all the equipment and the installation, the chilled water loop conversion, the thermal energy management, engineering costs, overhead costs, and a contingency of 30%. What's not in the budget, and these are not what we're calling non-Mitten costs, building efficiency upgrades. We think every building on campus, if it hasn't been already, needs to be upgraded. We're not looking at the cost of new buildings. We do have some solar in the pilot, but that needs to be throughout campus, and also backup electricity generation. So we're not addressing those issues. Those are real costs, but we're not addressing them. Next slide. Okay, now, there are some unresolved and pending issues. So what are those? Well, we have encouraged our budget to be reviewed by a third party. It's finally getting reviewed. We do have some concerns about their approach to doing it and the objectivity. We have a meeting next Monday. Then on the 17th of December will be a cost update from what we've seen before. That was done in June, so we'll get an update on that. Clarification of certain costs, life cycle issues, is the equipment replaced or not? Is it 30 years or not? And then it says eliminate discount rate. Now, for every financial guy in the audience, you're going to fall off your chair when I show you this. But assume it's $100 over 30-year life cycle. Constant dollars is $3,000. 3% inflation, which is what the assumption's been, over that 30 years on the compounding, $4,758. And then the right-hand side, here's what was done. They took the 3% inflation and then discounted it 5%. So the net effect is a significant reduction in cost. So we're not sure what they actually did, but we're going to find out. There's one other thing on the incentives, the Inflation Reduction Act. We've got a new administration. Let's assume that carries over. That $250 million of our budget, we think could be reduced by 75 million, so it'll be a net 175. We're not sure if the proposed approach from MIT, from the engineering firm, qualifies at all. Okay, anyway, that's the quick review. I'd be glad to talk more about this online. There's a lot of detail, but if you have to remember just one thing, if we're looking on the financial side, the centralized system, which is what is being proposed, is much more expensive than our approach. And so with that, let me turn it over to Rick to talk about the technical piece of it. And again, if you want to talk more about this, my contact information's at the end, and I'd be glad to do that.
So now Rick is sharing his own slides. Good.
Yeah, so my name is Rick Clemenzi, and I'm actually a computer engineer by design, but accidentally landed in the HVAC and geothermal fields by helping out a friend one day. And just wanted to point out one interesting thing that has been a wonderful experience for me is that I've gotten, being the MIT guy in this crowd, I've go to all the conferences and gotten involved in all the research and development stuff. And I've ended up on the Binational Standards Committee for the ANSI CSA Binational Geothermal Design Installation Standard. So I've been working very luckily with 2 dozen top engineers across the country. and across Canada on these systems and learned an awful lot about them, even beyond what we have done ourselves. And we put in systems ourselves on a small scale, sort of to, make sure we know stuff to do products and development research and whatnot. But to us, this is about climate, first and foremost. You're familiar with this one on the left, of course, and this 2024 is looking to be a very bad year for climate, for temperature. But living in Asheville, North Carolina, and having just had 21 days with no shower because of Hurricane Helene and the destruction displaced from that, this graph on the right is so material. It's like, I've been watching these graphs of the ocean surface temperature, and I'm scared. And everyone should be scared. And after seeing how much moisture came up here from that hurricane, there's some serious changes afoot from that. So this, just to make sure everybody kind of understands what geothermal is, although it's just a small part of this proposal. Basically, you have the air and the ground, and there's a big difference between the temperature in the air, summer and winter, and in the ground, which doesn't change summer and winter. We're 20 feet down to 200 feet down is just a giant thermal battery. And so when you're trying to get in the summer, you're trying to air condition a place and reject heat out to 90 degrees. Of course, that's hard, whereas rejecting heat to 60 degrees is easy. From 74 to 60. That's like you're rejecting it to cooler grounds. Likewise, in the wintertime, sucking heat out of 60 degrees when it's 20 degrees outside is a whole lot easier. This is what heat pumps do. And heat pump's not a mystical thing. Like Sarah said, your refrigerator's a heat pump. So, refrigerator, dehumidifier, window air conditioner, maybe, or car air conditioner, they're all heat pumps. And in a typical residence and in a lot of classrooms and a lot of office buildings, that small unit like that is all it is. To scratch under the surface very quickly, just so you get the idea, there's actual equipment behind this. The system has two coils always, even your refrigerator, one in the freezer, one on the outside skin and below. A compressor and a regulator valve for a refrigerant. And that refrigerant, you can reverse it so you can get heating and cooling, or in the fridge you don't. And basically what the system does is it uses the basic chemical relationships of PV, is pressure and volume are proportional to temperature. So when you pressurize the refrigerant as a gas and you put it in this coil, you get a hot coil. And when you suck on it to lower the pressure, you get a cold coil. So you get a hot coil and a cold coil in this thing, no matter what. And then every time it moves a molecule of refrigerant around, it's using the delta heat of vaporization to suck some energy into the molecules, move it over, and then throw it back out. Or suck it in on this side. Sorry, where's my mouse? This side, and throw it back out over here. That's what HVAC is. The bottom line here is, though, that when you're running in the geothermal world, you're running these things near a coefficient performance of 5, which means for every 1 unit of electricity and 4 units that you're getting from somewhere else of energy, heat, like from the ground, it will produce 5 units of it, like heat out. This is what's called a coefficient performance of 5. And this is basically how geothermal systems run on the average, around that kind of efficiency. So you see, they're really efficient. For a little bit of electricity, you get a big bang for your buck. This is a 500% efficiency compared to like a central utilities plant, which is running around 100-ish. So we've been pestering them, as Susan said, or Sarah said, that we did this climate collab thing, Susan, since 2016, and they selected us because we were outsiders. We're not on the faculty there. And so we could sort of be a scratchy outside voice, and we have been that scratchy outside voice, pushing and pushing to get MIT on board to hopefully be leaders for rapid decarbonization. And the students, this was a graphic done with the students for how to apply heat pumps. These are just heat pumps applied to exhaust systems in labs, which you wouldn't believe how much energy is lost there. Heat pumps applied around the buildings. And I think campus engineering really kind of didn't believe this was possible because nobody's really taken it seriously until now. But it took so seriously to us when the costing numbers came back that Susan had seen, although I guess that was a little later than we started. But I saw this plan that they had for upgrading what John talked about, all this new hot water piping, which is very, very expensive to do because it has to be metal, steel. But they also wanted this giant thermal plant and these giant tanks up to 150 foot tall out on the ball field where I played softball as an undergrad there. And I just take that personally. I don't think we should be taking the grounds from the students, and I don't think a big eyesore of a thermal plant is what you need when there's a more cost-efficient solution. So they challenged us. They said, okay, do a test fit on these 6 buildings. They're a little bit unique, but they actually are a good representation of the campus, because this was from some earlier work we did, like Susan mentioned. The reds are buildings we've been studying before. And it turns out the blue ones are the 6 buildings in this study. And you can see they are really representative of the whole campus. The pool, especially W35 is the pool, new pool. And it's beautiful, new Olympic pool and whatnot. But it's just as bad energy-wise as a lot of the labs. See, these are the labs kind of start in here and go this way. And these labs have this just enormous energy loss out ventilation. Well, locker rooms, 100% ventilation, 100% exhaust, 100% makeup. So there's all kinds of heating and cooling going on there. The same with the pool. There's a lot of exhaust and makeup. And if you want to just kind of grasp this at a simple level, what we're changing in that model is the top here is the way energy has kind of typically been done in the fossil fuel world, where you had plenty of heat and all that kind of stuff, and it didn't matter. So you just kind of let energy be blown out exhaust stacks, and it didn't matter. Well, to electrify, it does matter, because we have to build a grid and all that renewable energy to make up. So the bottom model is where we're going. The use of heat pumps in this high coefficient of performance world, like 20%, that's COP5. So the idea is that you can use a whole lot less electricity coming in if you capture all that energy going out and put it back in the system. That's the fundamental principle involved. So we went through these buildings and laid out the whole program for them. These buildings, like I said, were a little unique in that these 3, the Rockwell Cage, the basketball court, and the Armory Castle on the corner of Vassar Street and Mass Ave, and the W32, which is where like the squash courts were when I was there. These buildings are not on the campus chiller loop. So unlike most places on campus, which are on the campus chiller loop, this requires an upgrade of adding some ambient loop piping between these buildings. We laid it out for them. We're trying to show them how to do that cost effectively, not in steel, like the industry does, the geothermal industry. We've been all over the roofs and all over the mechanical rooms of these properties. And we have shown them, for example, on this roof, there's going to be some air source equipment up here. It's a concrete roof, and a bunch of concentrating solar collectors. So we gain enough energy for all the hot showers that are needed in the various locker rooms and the pool and whatnot. You see that little nook up there in the student center? Turns out that building had chillers on it initially because it wasn't on the loop. And so we're going to use that space. It's now been vacated. We're going to use that space for some air source heat pumps. So this is not a geothermal system. It is a hybrid advanced thermal system, is what we call this in the industry. So we've gone all over the mechanical rooms here, and it's really wonderful. One of the guys on the team has an iPhone 7 or whatnot. It has built into it LiDAR, 3D imaging, and he's gone through and made 3D models that you can rotate them, all 3D. And we can show how the new equipment goes in. Like, for example, you might have to move one piece of equipment into space and put in a whole bank of hundreds of tons of heat pumps and various other air equipment and how it fits. And even some photo and then how it fits. This is the work of a sharp guy with some 3D modeling software. We've gone through each building, every unit, every HVAC unit in the building, and shown what is needed, what it replace it, and then what is needed for the recovery from the exhaust and the showers and all that kind of stuff. And we've laid out what it would take, just a minimal number of bore sites, like 5 to 6 sites around here, where there's plenty of room and could shift and whatever. And we'll come in with this angled boring, which is a relatively new being used process in this country, but there's some drillers, a driller on our team who did an MBA at Sloan, who is specialized in this sort of soft overburden situation that MIT has. And so we know we can come in there pretty low impact. And we've got a test site set up that we're trying to convince them to go ahead and run a test bore out here so we can, so they can see what all's involved. But the big win is that MIT and everyone else, don't want to single them out at all, has been saying, oh, it's going to take so much electricity. It's going to take so much electricity to electrify. And it's like, well, it's going to take some more, but it's not going to take that much more. And we proved it in spades hereby in every one of these buildings, except for the Rockwell Cage, which is very little more than a lit parking lot with some basketball courts, Every other building has plenty of power for this solution that we put on the table. And the solution we put on the table is the worst case of what we would call a rationally efficient decarbonization solution using the most air source heat pump that the power budget and the space would allow. Clearly, as you iterate this and you go into more geothermal, you'll get this number way down. But even here, we came up with 1.6 times the current power usage. And this has to do with, they get a lot of their chillers from steam off their CHP plant and stuff. So it's a little complex at MIT. But this is way below the 3x that they were saying and the 2x that they've been saying lately. We're way below that. And with the power budgets for all the buildings. And I just want to very quickly show you how we got here and why I come with such strength of voice in this field, even though I'm a latecomer to the field. This is the ASHRAE headquarters. ASHRAE runs the heat and vent mechanical engineers. They're all members of ASHRAE. And they took 2 floors of their building and outfitted 1 floor with air source heat pumps. And the red there, the power budget in red, and 1 floor with blue. Notice this is outdoor temperature. So this is winter over here and summer over here. Notice this blue isn't exactly well balanced. It's not the perfect design, but that's okay. You get the point. That red is a whole lot more power than the blue, period. Even a really high-end, best air source heat equipment, the geothermal is just that much better, and so it's worth the effort is what it boils down to. The big worst case is if people put in minimal code minimum heat pumps, this is what happens. You end up with electric strip running, and we will never be able to build this grid. Look at the difference in power that will take at the winter peak versus all geothermal. It's huge. And so people have studied this and come up with, even forget those bottom end air source heat pumps. Even if you use all high end air source heat pumps, the grid is going to cost almost twice as much to do it with air source over geothermal. So we're not trying to say you got to do all geothermal or anything like that, but you get the point. There's a real value in this stuff. And the value starts to be, I'm sorry, I took a slide out there. Huh. So another example, and so that's sort of the macro level consideration. This is the micro level owner consideration. Beautiful new school done by an engineer who had actually put in 100 and something schools before he did this building back in 2010. I think this building got constructed. And this is one of the first net zero energy buildings in the country, where it produces as much energy from its solar and a couple little wind turbines as it needs. Beautiful school, but he, after 125 or something geothermal systems, he had the guts to go and just say, I'm changing the formula. I'm figuring out how to do this more cost effectively, how to change the field and come up with better paradigms. And the field has adopted all these paradigms at this point. In a nutshell, he came up with this. Oh, again, that's just all those little units. That's how he does it. Little units, they all have little pumps right in them, little pumps built right in them. No central pumping. He's figured out how to do geothermal in Dallas at no additional cost. They have some cheaper drilling there. And by the time you add the solar, keep losing my mouse. By the time you add the solar, the net result is these schools make money. These schools actually make money off their HVAC systems and their solar and wind systems. And it's just kind of a radical departure that your building is not an expense in the classical sense, but it's actually a moneymaker. And so this has all been proven. NREL has studied these things. These things have all been shown to be what they are. And if you want to think at a macro scale, although the money is now showing up, unless somebody goes and erases everything that's going on good about green banks and everything right now, which who knows. But you, even without the green banks and without the IRA, the money is already there, because right now, if you think about it, everything you do, everything you buy, everything, just about, at least up until the last couple of years, has depended on fossil fuel energy, period, to get it to you. And so as we make this transition, we're transitioning to this. We're transitioning to energy from the sun and from the earth and getting rid of the link to the fossil. And so when we cut that out, that's all the money you need. And in fact, this has been proven now by the Colorado Mesa University and some other players who have, once they've invested like electric co-ops, once they've invested enough money for 5 years, they have found that all of a sudden the systems start giving them a return on investment to pay for the rest of the transition. So the trade-offs are there, right? It's a little more expensive to install, But right now, Massachusetts actually has these incredible $4,500 a ton rebates. And the IRA would give another 40% off for MIT if that still lives. They're less expensive to operate. They're less expensive to maintain, it turns out. These little systems, like Judy and I have a lot of systems we've installed we have never been back to. They're so just reliable. And they're less expensive to replace because all the equipment's indoors when the geothermal part, it'll last longer. And the grid is going to cost less for all of us. So that's like a demand charge for commercial. And so why wouldn't you do this? It's kind of, why wouldn't you do this? And it turns out the reason is because it's more complex design engineering. It requires another set of learning that engineers have to go off and gain. And unfortunately, it's a real challenge to get the engineers to do that. So the conundrum is that we all have the moral responsibility to do this. And I think people do kind of get that at this point. But there's perceived complexity is a big barrier. And the training is available. The training is available. You just got to get the engineers to go there, or you got to bring somebody on board in a project who has this knowledge about these systems. Like, this is how this has happened. We have 2 people on board in this team that have this knowledge. And so what we're trying to do as a bigger part of the project to moving forward past this is that we are, Susan, and we are developing an inroad style interactive simulator to try to make it so that lay people can show building owners this solution without needing expert advice. I don't want to get into it in any kind of detail, but the point is we're building this inroad style interactive interface, and behind it, of course, is a complex model. Thank you. Back to you.
Beautiful. Okay.
Thank you, Sarah and MIT Alumni Association. I'll give a brief intro before I dive into stakeholder engagement. I graduated in May, and I've been part of the Geo to MIT team with Jason and Olivia since last fall, after responding to Susan's call to get involved with campus decarbonization efforts. I have been on student governments for the past 4 years, so I have some experience with working with administration and staff on various campus initiatives. I have also worked with Office of Sustainability over the summer on student engagement, and I'm currently working with MIT Environmental Solution Initiative on climate education and student engagement. So I'm here to talk about stakeholder engagement, and namely how alumni can and should be involved as stakeholders for the climate, for the campus decarbonization process. So thank you, Susan, for this slide. So right now, there's currently very few students and alumni who are aware of or who understand MIT's campus decarbonization efforts and timeline, and even fewer are actively engaged in decision-making. So as I mentioned, I'm hoping to answer questions: why should students and alumni get involved, and how can we get involved, and what can we offer? Next slide, please. Okay. So right now it's a crucial moment for MIT's climate action, and so thus an opportunity for influence and impact on our side. We have President Kornbluth, who is a champion for climate action. She spoke about that at her inauguration speech. She also has launched the MIT Climate Project in February, and there will be announced that there will be a new Vice President of Climate, which will be announced and chosen by early next year. And also we are in Boston, in Cambridge, which Boston and Cambridge both have very ambitious climate action policies. So this works very well for things that MIT and we want to do for advancing decarbonization. And right now, because of there's so much attention on climate right now, they're asking for input, and they're looking for input on operations decarbonizing MIT's campus by 2050. Again, we want 2035 on education, really advancing climate-focused curriculum and programs, and also research supporting sustainability innovations. Next slide. So why should alumni and students get involved? Well, we're uniquely positioned to shape MIT's climate future. There's a shared legacy and responsibility after having gone through MIT as a student. We really embody MIT's values and spirit, that spirit of innovation. That's why they admitted us, and we have worked a lot. MIT has been our home, and we really share that deep connection with the institute, and thus have a vested interest in its future. It's our community, and we'd like to give back, and we can work with our community to make impact on the world. And also we have the ability to drive change through expertise. Again, we have gone through our MIT and have education through MIT, and then also have a lot of alumni have worked decades in their area of expertise in industry, in research, in governmental, et cetera. And so we can really use our experience and our expertise to advocate for bold climate action leadership by showing ideas of how MIT could really lead in sustainability and decarbonization efforts. So I'll talk more about this in a bit. And we've been really trying to drive home for MIT and for alumni and students all around, like why it's a win-win-win situation for working together towards on MIT's campus climate activities. So for alumni, again, we can really reconnect with MIT through meaningful engagement with a shared purpose, really making impact on the world, and also have the opportunity to mentor and empower students and really leave a legacy in sustainability. Like working across generations is really helpful. And we've from this experience, I've learned a lot from alumni, and alumni have learned a lot from students. And on the student side, they get to experience working with alumni who have a lot of expertise and really share ideas. And they bring fresh energy and really hope. And I'd say from all the adults I've talked to, they one thing they love to say is youth have a lot more drive. They have a lot more energy. They haven't gotten jaded from being told no too much. And so it's really inspiring to see youth have all that energy, and alumni have a lot of critical thinking and working together to problem solve this. And for MIT in general, both staff and students and faculty and administration and alumni, we really can set a global standard for collaboration for sustainability challenges across generation, across expertise levels. And we can really inspire and support bold climate action as a community. And lastly, by working together, we expand the capacity for brain power, resources, and innovation. And with this collective effort, it's a multiplier effect. We can really drive innovation and advance sustainability at a greater scale. Next slide. So we're using the Mitten project as a case study of influence and contribution. I'll outline how we made this work, or how this worked, and then again, this shouldn't be the only situation that is happening. The Mitten is one case study out of many, hopefully to come in the future, of alumni and students contributing. But alumni expertise sparked opportunities. Rick had with his decades of experience proposed MIT thermal energy networks and was really able to connect MIT with ideas with geothermal and also with other geothermal experts. We ran into challenges of outdated education, but we were able to, we are currently working on really accelerating that research to implementation process through conversations with staff and faculty and administration, students and alumni, creating and beyond, even outside of the MIT community. We've been creating comprehensive proposals to share our ideas and offering MIT classes to teach students. And so we've noticed that there's there's always going to be innovation. There's always going to be the education that is needed to match the implementation with the innovation. And so we really try to keep that in mind and accelerate that process because we're aware of it. And we try to work with MIT also to learn about MIT's and considerations and constraints, which we will hope to problem solve around. Innovation and future thinking also needs to be matched with the present. It's how do we get from point A to point B and accelerate that process, what we're really trying to focus on and keep in mind. And we continue to be really persistent in contributing. Oh, sorry, could you go back to the slide? Thank you. And we continue to be persistent in contributing to the campus decarbonization process, really sharing what I shared with you guys in the last few slides. This is why students and alumni need to get involved. We can make an impact together. And these are some ideas that we have. So really staying on top of that is and trying to carve a precedent for more student and alumni engagement. I know Sarah mentioned in the beginning that students and alumni were why MIT first made their climate action plans back in 2016. So what we're trying to do is really just empower alumni and students to contribute meaningfully to campus climate action, ensuring our voices, ideas, and skills can be leveraged to drive MIT's climate action forward. So we try to collaborate with MIT as an institute. We try to learn, share, educate, and scale through our reports, producing competitions and presentations. And then we try to increase awareness and engagement around campus decarbonization, like this webinar is supposed to be for. And we are presenting our stuff, our work to a global audience at the International District Energy Association's Campus Energy Conference on Accelerated Energy Transition in February 2025. And this is because as we work at MIT's campus, MIT is a microcosm of other campuses and other institutions. And so we really want to show, we can work with your community to make climate action, and MIT is our community. And still we can learn across communities. There's a lot of parallels and similarities and differences that we can just learn across from MIT to the global community as well, and vice versa. So we will be presenting on these 4 presentations at the conference. And if you want to learn more about those, there's a link of our presentations that will of our posters that we'll be presenting. And by that, I think that's, and to close it off, what can you do? Basically, we want more of this. We want more alumni and student engagement, and we want to be able to channel ideas and work together to make an impact on MIT's campus and beyond. Mentorship is a great way to do that, really giving advice to youth, supporting students, advocating to expand alumni and student representation in climate decision-making. You can sign your name on letters, join working group meetings, etc. You can submit ideas. We're hoping that there will be more infrastructure to support idea submission. Sometimes it's like there's an idea, but also there needs to be the work behind it. Really streamlining that would be great on all fronts, not just from students, but also from and alumni, but also from the staff, etc. And so we hope to work together with MIT to do that. And then also, this is an idea of really, but potentially if we need to, then we can possibly make a specific funding for decarbonization initiative with conditions for alumni and student involvement. Because with funding, you become a larger stakeholder. And this QR code, you can scan it, and you'll be led to a form where you can sign up for a newsletter and get more involved, and really indicate which areas you'd want to be involved with, and we'll reach out and try to work together with that. Next slide.
Yeah, and so I'm just going to close with a few more slides and say that what's been paramount for us for the past year has been to demonstrate on the MIT campus that the proposed Mitten plan can actually be a pathway for the decarbonization both of these 6 buildings, and then a stepping stone to decarbonization of all the campus. And as we say, we think that it can be done by 2035 if MIT would embrace and act. We have been active in an education and starting a media campaign in the last months. 100 letters have gone out to what we call key influencers on the MIT Corporation, on faculty working groups, on the climate nucleus and other facilities, the Office of the Vice President, to the Treasurer, Chief of Finance, and we are setting up a website and starting to make our material more widely known. We will, for the 2nd year, offer an IAP class in thermal energy networks, rapid decarbonization of campus, and it will include 3 field trips this year to zero carbon or low carbon buildings in the greater Boston area. And we're very excited about a new special course. Rick mentioned the CGD, the Certified Geothermal Design course. 4 members of our team have taken that course, a 10-week online professional training course that started in October and finished today. And we are going to draw on that in the syllabus of the new class that Rick and I and a number of the members of our MACA team, as well the CGD course teacher and his colleague have offered as of a meeting earlier today to also join in guest lectures in this course. We have references for the reports, our latest reports, and we have now come to question and answer. Megan, this QR code is for what?
That is the same form that will lead to a,
Same form. Okay, great, wonderful.
Mhm.
And if you have questions, John Dabels is our point of contact for this work. I think that's everything. Did you, Sarah, want to say anything?
No, at the end of our conversation,
Okay, okay.
So in the chat, let's see what's there. Well, first of all, since you were just speaking, Susan, they were wondering if the course was going to be available online, your course that you're giving.
I think
But
not.
you know what? People can unmute themselves to ask their question if they'd like to.
The class will be recorded and it is going to be put on OpenCourseWare. And we hope after our first sort of dress rehearsal year, our first kind of learning year, that will be on MITx the following year. That hasn't been worked out yet, but what I can say is that there's almost no course like this that exists anywhere. The people who teach the CGD course have 40 years experience in this industry. They have been teaching it to professionals. They have made an attempt to teach it at a university in Canada that fell through. And so they're kind of excited about the opportunity to co-teach it with us. It will be a very valuable experience. But no, yeah, it will only be in person for the first year.
I'd like to just pick one out of the chat. Billy Roberti, I think I'm saying it right. You had some questions about ground temperature, etc. Do you want to put some comments in for us on that?
Well, I work
Nick.
with geothermal installers on Long Island, and they're saying the underground water temperature, hence the ground temperature, is 53 degrees. So I was wondering where the 60 degrees came when you were in Massachusetts.
No, it was Rick. Rick is in North Carolina.
So the way the system works is you're 20 feet to 200 feet down, okay? That temperature is the same as your average air temperature where you are. And it'll even
Well,
change
it
your
just
mountains, the north
turns
side,
out
the
that
south side.
when you measure ground temperature up here, it's about 55 degrees.
Yeah.
So
Because that's what your average air temperature is.
I guess so. Thank you. Yep. I
It's
haven't
thermal
seen
balance.
average air temperatures lately. So
Yeah,
Billy,
well,
that's good that you've worked with some of the folks on Long Island. That's have you actually done installation or did you put something in?
I've had a geothermal system since 2011. Love it. That's how I got involved.
Is it a ground source or is it an air source?
Oh, sorry.
It's a unique kind of geothermal system.
Which is?
Not available, so I really don't want to talk about it. It's no longer available.
Oh, okay.
Not as
The
successful as
reason
we
I
might have
ask is
liked.
because I have something, I have a standing column well, which is sort of a hybrid between an open loop and a closed loop system. And it's New England is a good geology for this kind of a system, but it's not widely known across the United States. So I just wondered if you, and I
Yeah,
come from Long
well-
Island, so I was interested in what was going on in Long
Well,
Island.
that's exactly how St. Patrick's Cathedral is heated and cooled. They have standing column wells. Of course, all that bedrock in Manhattan. Long Island is mostly sand and clay.
Of course,
So
yes.
we can't do that, but we use mostly closed loop systems.
Yes, I've spent all my growing up life on Long Island, both in Nassau and Suffolk County, so I know it fairly well.
Great. Tom Mikas, you were talking about redundancy. Will you come online and ask us about that?
Yeah, I've had a geothermal heat source two pump system in my house since 2014, and there were a couple installation issues and a couple operational failures over the years, and it's been very handy to have the two units because at least half the house can be heated and then the fans kind of circulated around. So I'm wondering how that applies on campus. Do you have redundancy if a specific unit fails? I hesitate to wonder about any sort of system failure, but what about redundancy?
Well, we've even gone one step further to just really challenge the concepts here, since this is sort of a test and a way to educate. We have actually specified several of these unit replacements as clusters. So like you might replace one big air handler. You know, these big air handlers, these giant things are like 8 foot by 8 foot in these commercial buildings. And they have flat coils, so they don't have a lot of coil in them. And the way these geothermal systems get more efficient is to have more coil in them. So replacing them is you don't do a one-to-one. You need to be able to get more surface area and coils, and one way is to put in more units. So that's actually what we've proposed, is put in like clusters of units behind a cluster controller. And so the BMS system for the campus just sees one unit still. And but we guarantee redundancy and, you know, fail safe and all that kind of stuff.
Cool.
There's a hand up. Go ahead.
Yes, hi, I'm Max. I'm calling from Zurich, actually. It's late here. I had a question about the very first, I think maybe the very first or second slide of one of the presentations. It said 97% of MIT's CO2 emissions are from buildings. And I was just wondering how that was calculated. Does it include things like scope 3 or is,
It's
you know,
scope 1, and
I see.
it includes the electricity and the building loads. Is that correct, Rick?
Yeah, and it's about 1/3, 2/3 electricity building loads.
And by building loads, you mean heating and cooling?
HVAC, yeah,
HVAC, yeah.
HVAC,
What do
which
you
is
mean
off the
1/3?
chart.
Rick, what is 1/3? 1/3 of all the BTUs, 1/3 of,
1/3 of the carbon emissions is essentially attributable to the electric generation, because remember, MIT generates their own electricity.
I see.
From- from gas.
So when you're talking about electricity, in this case, you're talking about scope 1, like it's electricity that's generated on the MIT campus.
Right.
so
And
wait,
this
so
is
90,
interesting. It's an interesting
what's the-
dilemma for them. Just a second, Sarah. It's an interesting dilemma for them because they've been saying, oh, well, our cogen plant is more efficient than the grid in New England. And we're right now in this transition period where people are watching their grids become cleaner. And so they're actually being challenged that right about now, the grid is getting more efficient than them. So it's really putting a pressure on the situation. Sorry, Sarah.
I don't understand. 97% of the carbon emissions are from the buildings. Does that include the turbines at the central utility plant
Yes,
that are making electricity?
that's where it's all basically coming from.
And the
Most of it-
citation is from the MIT Office of Sustainability website. So if you go into MITAS, you'll find this reference somewhere.
It's not quite worded right, Sarah. It should be attributable to the buildings. In other words, the
Okay.
power and the heat and vent, right?
Okay,
Not-
because they put 2 new combined heat and power gas turbines into the central plant. They were only started up in about 1997. I mean, 2017, sorry, recently. And MIT has a very big concern about having enough electricity and having constant electricity because of its laboratories and it needs to have backup power. Apparently, they only use one of the 2 turbines in general. They don't need to use both of them all the time. And I don't know how they switch from their own electric generation to the grid, but they do use the heat right now from those turbines to do the current steam system. And that's that. So they have a network, they have a district heating system already. It has just a steam loop. Well, it has a steam loop, and then they have a separate loop for chillers in the summer, which are all electric. And I don't know if they run their gas turbines for the electricity in the summer or not. So
Oh,
that
the turbines for the power all the time. And so they're
But they
actually
don't-
generating, part of their chilling is from steam powered compressors.
okay. That's silly, Mo.
Max, did we
sorry,
answer your question?
Yeah, just to sort of follow up very quickly to Rick's clarification. So you said that currently, if I recall correctly, you said it's like 1 to 3 of electricity versus, but when you say electricity, do you actually mean like sort of lighting and computers? Because I
Yeah.
assume that some of the HVAC is electric too, right? Like the actual air
Oh,
conditioning.
Yeah, there's electric in everything, but there's electric in everything. So the point is that of their scope 1 emissions, it's kind of, I don't remember the exact numbers, but it's kind of like that, you know, it's about 1/3, 2/3, 1/3 for the electricity needed for everything. And then 2/3 for the heat and cool needed for everything. In other words, you know, they don't get all of their heating and cooling off just the electric generation. They actually supplement that with more gas and more other things to get steam. Steam's a very energy
Sure.
loss-based system.
They don't
Yes.
have any electric heating, so as far as I know, there's no electric heating in the buildings, although they're starting to install a few air source heat pumps. So that's using a little bit of electricity, but not, there's no resistance heating and there's no, they
Yep.
use steam. So their answer so far for decarbonizing has been to go to hot water, which doesn't need, you know, the extra energy for steam. And they're starting already to build piping for hot water that they're going to use for heating. But of course, that can't be used for cooling in the summer. The nice thing about the way that Rick and John and everybody on the team has designed this is that since there's both a heating piping for the radiators around the school, and it doesn't cover all the buildings either, but since there's already one pipe for that, the district pipe, there's also a district pipe for cooling. So I think, Rick, what you're doing is taking over the cooling pipe. Which one were you planning to
Chiller
use?
loop.
Exactly.
chiller
That's
loop,
what it's called. It's a chiller loop overbuild where you go, well, you got a loop there already. And we
Right,
did
right.
the math several years ago. I did the math with those experts like Ed Lorenz and whatnot.
Yeah.
And yeah, basically the amount of capacity needed to heat or cool the buildings is there in that chiller loop. If you use it as a neutral loop that's used for both heating and cooling. An ambient loop, that's what that term is, ambient loop. It's the same pipes.
And then you don't have to redo the pipes. They are starting to install hot water pipes now.
Yeah.
In the slum
So-
portion of the campus, they have, yeah.
Steel piping is the big bucks. It's like, you don't want to do it if you don't need to. And this is one of the challenges, is that this class of engineers, they've been brought up in central plant engineering, you know, this is what they've done, is steam and everything. And so was an interesting thing that happened. That, you know, they went, oh, we're going to change, we're going to get more efficient and get rid of the steam system and go to hot water, medium temperature hot water. This is kind of shocking to me. Medium temperature, that means 180 to 212. And it's like in our world, like Colorado Mesa, this place that's now fully decarbonized, and they're so decarbonized that the electric company came calling and said, how have you guys expanded your campus? They like doubled the size of their campus and their power demand did not go up. And so the electric company came calling and said, how did you do that? Well, that was a geothermal system. And so these systems are just that much more efficient, but the entire Colorado Mesa campus uses no hot water from heat pumps over 120 degrees. And that's like a concept breaker to somebody who works with steam. They just go, well, you can't heat a building with 120 degrees. When the answer is, of course you can. You just have to design for it.
Yeah, I think the other thing
But at
that's
radiant floors, we do it at 105 degrees because it's even much more efficient. You just design for it. Good job.
well, I think the other thing that's happened, I mean, you got this engineering mentality of how do you get over that? I mean, you encounter that in, you know, a lot of, I mean, I come out of automotive and we encountered that forever there. But I think another thing that helped was then the non-design engineers began to look at the cost difference. And the letter that, you know, we referenced that we sent out to 125 people emphasized some of the cost numbers that we talked about in this presentation and said, guys, you know, here's how much more money you're going to spend. And some people, can't say how many exactly, but began to call different people on campus. In fact, what we got, it was really funny. I got a letter back. I ended up signing this letter for the team, but we got a letter back that said, from who will go nameless, who sent this, but please stop sending the letter. You know, we're getting all these calls at our office. So just making people aware both on the technical
They
side
set
and
up an
engineering.
appointment to see us, didn't they, John?
Right, well, yeah, that also.
We handed in our report in August and we hadn't heard from anybody until last
Right.
week.
And so it's like, okay, guys, but I think part of it is not only the engineering side, but then making people aware of its cost and what does that mean long term. So we've seen this sort of dual approach here.
Yeah, there's a question from Michael.
Hi, thanks. Great that you're doing this because I've been trying to work in this area, talking with MIT, for 10 years and like, don't bother us, we're the experts. 2 points. One, you have to be really careful. These buildings are already built, so the heat exchangers to provide heat, during the winter time has already been established. So 120, I suspect in many buildings isn't going to provide sufficient heat on the outside perimeter. So you might consider what happens if you want to supply 150-degree water. And, you could do it for those days that it's very cold, you could have an electric booster heater. But I think you can't just use 120-degree water to meet, building heating loads in Boston. Second issue I want to bring, and I'm glad to work with you guys because I'm across the river at BU and we have an all-electric building. And I've been looking at buildings at BU for the last, 10, 15 years. Second issue I want to bring up is related to that. Until you get the C-suite, the executives to want change, it ain't going to happen. So I'd love to hear you guys talk about why do you think you have credibility now within the C-suite, the CEO, CFO, that, we've at BU, we didn't really start doing things until Bob Brown, the president at the time, who was, from MIT, said, I want to develop a serious climate action plan. Nothing happened in spite of all the people pushing for it. So I'd love to hear your comments on how you think you're going to get into the C-suite and get her to say, I want this 2035, goal, because the bullshit has been flying about, oh, by 2050, all the research we do is going to remove more carbon. That's baloney. We got to do it in our own houses. So I'd love to hear from this group.
So I want to jump in on this because I happen to have a house that is very unusual. It's in Swampscott, Massachusetts. It was built in 1910. It was built by an MIT architect class of 1873 who had an architecture career. And it's exactly the same vintage as the old campus. And I jumped into the decision when my husband and I bought this house, which has got a museum in it for my husband's work, and is 10,000 square feet. So it's like a big dorm or a big campus building. And I thought, if I'm going to live in a house like this, I want to take it as close to net zero as I can. Starting in 2014, I have converted to solar PV, solar thermal for the hot water, and 2 geothermal heat pumps. And I've reduced the natural gas use in the house by 85%. And I have one more step to go for the 15%. But when I got this far, it dawned on me that if I, with my relatively limited knowledge of this field, but learning as we go, can do this in a same age house as MIT's house, then MIT can do it. And so that's where I've kind of gotten my passion for this project. as regards getting into the C-suite, I don't think that Sally Kornblith is going to be the person who's going to make this decision. I think the decision is going to be made by the financial people and by the Vice President for Campus Services and Sustainability. He has offered to join me in this course, as he has guest lectured in my classes in the past. And we are on good terms with him. I'm not saying that we've convinced him yet. I think that what will be the most convincing is if we can get this pilot up and underway and demonstrate that the proof is going to be in the pudding. And I think that's where we're going to start to really make a difference.
I'll also,
Well, and just something that you all might appreciate it is, again, not to name any names, but along the way, somebody used one of our slides without giving us credit and tried to discredit us and to make sort of mock of what we were presenting. And all they ended up doing was showing their hand that they didn't know what they were talking about. And so that got back to campus engineering. And they learned that we did know what we were talking about. And that's when they gave us some memorandum of understanding to do this. So I think there's at least some people in the school who realize there's at least validity to learn something here. Where they'll end up going is a different question, but they did learn that it's worth learning. That's a big step.
Yeah, the other thing is we did hit a couple. We intentionally did not send the letter to Sally. That was a conscious decision. But there are several C-suite people who have responded. So I think we're inside the C-suite. Whether we get final approval or not.
Establishes the her budget priorities, and that's what gets funded until it becomes her and the rest of the executives their budget priority. They're spending money building other stuff, so you got to get it, in my experience, on her desk and her to say yes. It's not really a financial. There's like $1 billion of repairs that need to be done in MIT buildings. It hasn't been done, so it doesn't get done until someone has it as a key objective. So yeah. I'd urge us to figure out those ways, either through the corporation, or you think you're going to do it through the finance person, but it really has to become a budget priority.
No, we hear you, and we're now. I don't want to imply we're all the way there. We have made huge progress versus what we were, because we were getting, it was like pushing on a string. That's where we were. Now their MIT portion of it is pulling on a string and saying, "Come on along, we want to learn more." Now there's another step or two beyond that. But as Susan talked about, I think getting approval for the pilot program is a major step, but there's also a couple more. And believe me, I've been through a lot of these myself outside of MIT. I understand what you're saying, totally agree with what you're saying. We are making we are much farther along getting final approval than we were, a month and a half ago.
Oh,
For the pilot.
Yeah.
And only for the pilot.
Well, we also talked about other things as well. I think who knows exactly where we are. We'll find out in the next couple of weeks. We'll have a whole lot more information, but we have presented both the pilot and a comprehensive concept, or a concept for the campus. Let's put it that way.
And to Megan's point, sorry, Megan, you can make the point.
Go ahead. This is the same point you're going to make, but I was going to say, we are asking for 2035, but also we have a tangible solution that they'll have to analyze too. It's not that we're just saying we want this goal, you guys get it done. We've done the work too, and I think that they will really respect that, and it'll get something tangible for them to actually critique and say whether it's not possible. And I think having more people on board, and now you guys are all aware of this, will also put more pressure on them to consider it more carefully, and for them to realize how important it is to the community, both students and alumni. Right now, I wouldn't say a lot of students really realize this is happening, but that's we're also in parallel doing that, like working with Student Sustainability Coalition, UA and GSC, Sustainable Charter Student Governments, really gathering the student awareness to really put a pressure on this, because they already said that they care. That's why, like, Sally Cornblow talks a lot about climate. They have the climate project. It really is, it's something they genuinely, and I've worked with a lot of staff and administration on this, they generally do care. And so if there's a way to make it possible, like they seem very open to it. And we really just need to also understand what the other factors are that are being considered outside of the realm of just campus decarbonization. Because I do recognize your point. I didn't see who's speaking about how they have a lot of funding on different efforts, and maybe the funding isn't budgeted for right now, but how do we accelerate that? That's a question that we need to ask. And hopefully that will be answered on.
I was actually making a different point, which
Okay.
I'd like to make. And that is, our effort working with Susan and all reached a quantum leap when Megan got involved, because Megan is unafraid to go knock on any door and walk in and talk to them. And so likewise, it's made a quantum leap as John sent out these letters to the CFO and people like that. And so don't doubt your power of getting involved and making sure that your voice is heard, that you think that MIT should at least be paying attention to the cost of these, and more importantly, from Judy and my point of view, the leadership potential. Because here's an opportunity for MIT to still be a leader in this area of buildings decarbonization that just doesn't seem to be an important thing at all. And for the world, it could be a very important thing.
Not to mention the Cambridge's Buto Act that will tax buildings after 2035, and so they have another incentive to decarbonize by then as well, which I'll send a link to you guys to read more about.
Megan, I think it's worth. There are a couple other questions in there, and nobody's hand is up though. But you had on the form that you have. I've just put the form in the. If you want to think about signing letters, making letters. Megan, if you would go to your form and just say some of the things that we're asking you participants to see if you want to be involved with. Just go through the list. I'm sorry, I can't pull it up at the moment.
We're still discussing on the next steps, but definitely we had an Earthshot letter that we sent out in May, which I still need to send an update on. But that one we asked for 2035. We asked for more intermediate deadlines. We asked for more student engagement. We're planning on I'm working with some students to do another round of that to really get more people involved. Sally did receive it, and President Sally did receive it, and it did show the staff that students do care and alumni do care. I think sometimes and then now they're also working with staff, sometimes they don't realize how much support they have on climate, and there's a lot of different stakeholders involved, and some people do not care about other things more than climate. And so we really need to show that we really need to stand behind them and give them something to look at and be like, hey, there's someone over there knocking on a door about this. It's important. It's not just me, a staff member, who's saying it, but also the community wants it. So it's very
great. And that's what the people on the webinar right now, I think, are people who are more interested in the MIT alumni campus team of MACA. So those questions that you had on the form for how people could get involved, why don't you you read them off? Just so I put the form link in the chat, and I guess we could all go look at it. I could even go look at it.
That's good. We also listed joining the working group meeting, the MACA campus working group meeting for Mitten, and we're in discussions of creating a new working group to improve student alumni engagement with MIT's broader climate action. That was something that Sheila has been thinking about, but also and Sarah has been thinking about, but also Tom Kiley has been thinking about, especially because okay, I won't go on a tangent on that side, sorry.
Tom Kiley is inside MIT. He's been helping with their climate plan for 10 years now, since the first one was issued. Go ahead.
Yeah, he's a great he's one out of a few people working on managing the climate project right now. We also want to do more giving updates about our work by email or more Zoom discussions like this. mentoring students. There's sometimes a disconnect between like alumni wanting to get involved and then and students who might want alumni expertise, and we're thinking that connection can be really helpful. And also submitting more ideas, like, and I know people have been sharing ideas through the chat, which will be very which we definitely want to explore more as well. And then again, like the donating idea is a bit of an interesting one that we're kind of thinking about, but it's unclear yet how that might come to light. But the idea is like if we can be like, okay, alumni will support this much of a campus decarbonization process, and maybe that will make it enough where they will consider it 2035. But of course, we want to be aware of making sure that they're not just like that the MIT, if alumni donate, like there isn't a lack of like less of a responsibility for MIT to also contribute. And so that might need to be done carefully, but it is an idea because sometimes funding is the limiting factor. So it's definitely more discussion that need to be done among the climate folks at MIT. And it's just to understand the different stakeholders involved.
Actually, I know that from 10 years ago when we did the push to, there was a fossil-free MIT movement, a lot of people stopped donating because they didn't think MIT was doing enough on this issue. It is very possible we could round up quite a few alums who are interested in, if MIT makes the commitment, just like Mr. Gelber said, if MIT's top people are committed to getting this done and done right, it is possible that more alums would come back and be more interested.
I didn't know that. Thank you for that. But yes, any questions on the ways to get involved or any additional ideas to get involved? Definitely always looking for more.
I want to thank everybody for coming. And are there any questions, pressing questions that weren't answered in the chat? Please speak up now.
Asking for money?
Well, that's the issue, donating. Asking for money, MIT does all the time, but for particular purposes, if we know what they're going to do with it, that might be a good idea.
Well, and if you wanted to support this Mitten project, we're trying to get this piece of software out, and you know, it's happening. I'm going to get it out there. We got to change the world somehow, and accelerating getting past the stick in the mud engineers is got to be a big part of it. Just what we've run into and realized it's in our local thing. It's at MIT. It's everywhere. It's not pointing a finger at anyone in particular. It's like an inherent thing in the engineering profession that it's fundamentally geared toward holding on to what's been done for 20 years. It's well proven. It never goes wrong. You don't get mud in your face. But you know what? We didn't have a shower for 3 weeks. So it's like, you know, climate is a different demand. And we need to, and I think all of us have an opportunity. That's sort of why Judy and I came to MIT and did this back in 2016 initially, before even meeting Susan, is that we think that MIT is in a perfect position. We think we all are in a perfect position. Talk to the people you know and influence. Tell them there is a way to decarbonize. And not only that, it'll save you money. People don't know that. You know, like in our city here, we hired the head of the city council, county council ended up being a guy who retired with a bunch of big bucks from one of these solar firms that built up in North Carolina. And so in the county, they realized that it's like, well, solar is a moneymaker. And so they went after putting solar on all the schools and everything. They stopped at like 40 buildings for year one, and then they've added more since. And every one of them was a profit from day one. As soon as that power was turned on, they were in profit mode. That's the economics of this stuff at this point. And that's the reality of the situation and the opportunity for rapid change. But people need to know it.
Okay, Mr. Rajivan, would you unmute and give us your questions?
I'd put my questions in the chat because I couldn't raise my hand.
Can you just tell us the questions, or should I try and find them and read them out?
Okay, let me see if I can find them. Hang on 1 minute.
Finding them.
Yeah.
One of them.
Huh? Yeah, go ahead.
One of them was about energy efficiency solutions. I think, as John was saying, we're not counting the things that MIT should be doing anyway on its own, normal plan, and it has been. They've been doing much more energy efficiency. The new buildings are all some level of LEED efficient, that kind of thing. So that's one of your questions.
Right.
But if you found another one, go ahead.
Yeah, I was wondering, my first question I think was, what was the absolute cost of the two proposals? I know
The
that
absolute cost for, okay, the absolute cost for the consultant's proposal of their top pick. And this is from their June presentation. And they will be giving a presentation on the 17th, and it will definitely be updated. But the cost was 1.25 billion.
Yeah, that cost is comparable to what we're doing. Actually, they have more costs than that because they picked up buildings, rehabbing all the buildings and so forth. There's some other costs, but if you want to do an apples to apples comparison, that's exactly what Susan just mentioned.
I see. And the second proposal was 700 million less. Am I right?
I'm sorry.
The second proposal, our distributed Mitten proposal, is 700 million less.
Oh, yeah, that's right. Yeah, and now, that's an estimate. Okay, we're dealing with estimates on both sides.
Right.
And we're trying to figure out exactly what's in what bucket and, how they assumed this and that. But we're comfortable that that's relatively close. It might be 50 million off plus or minus, but at 700 million, it's an order of magnitude. It's correct. And it's enough to get somebody's attention that we need to look at this. What's the difference? But we've been very conservative. By the way, we've been very conservative in those estimates. So if we had to, say, well, let's take A or B, we took the lower number and had a higher cost.
If I could, we're coming to 7:30, so some people have planned on leaving at this point. I just wanted to thank you all. The EES network is just so proud of what MIT alums are doing everywhere. A lot of the MIT clubs have subgroups that are looking at climate or offering programs. Our network is a way to help spread information among all these groups. MACA has had some very good active programs, whether it was that first letter they wrote. There's another group called Climate Education and Advocacy that offers En-ROADS simulation workshops around to anyone who wants them. So there's a lot of stuff going on, and we are at the EESN.alumcommunity.mit.edu, and MACA is part of the network. It's an alumni group doing some great things. So I want to thank you all for coming. I hope you'll keep an eye on what we're doing. We try to make sure that there's at least one good webinar each month on one of the topics. It could be environment. We generally are not looking back at MIT. MIT does its own promotion, et cetera. And MACA is very good at keeping track of what MIT is doing. So if that's what you're interested in, talk more with Shill and Megan and Rick and John and Susan. So I want to wish you all a nice holiday. It's solstice season, and actually December 21st is Chester Greenwood Day. He invented earmuffs, they say. He was a Mainer, down Mainer. But up here it finally has gotten cold. So thank you all for joining, and
The
unless
opportunity.
anybody on the
We
panel
really
has
enjoyed sharing it.
something to say, thank you very much.
Thank you.
Thanks for coming, everybody.